You are listening to the AI World Podcast, your trusted source for the latest innovations, insights, and trends in artificial intelligence, blockchain, fintech, and decentralized technologies. Each episode features expert interviews, engaging discussions, and in-depth analysis of how AI transforms industries worldwide. Stay ahead of the curve with the latest articles and exclusive reports from the AI World Journal, covering everything from emerging technologies to industry breakthroughs. For more news, global events, and access to AI World Society circle gatherings, visit us at aiworld.tv. Don't forget to subscribe to stay informed, stay connected, and be part of the AI revolution with AI World Lounge. Thank you for listening.
You know, whenever we sit down to talk about this explosion in artificial intelligence, we always seem to gravitate towards, well, the same three things.
Right. The usual suspects.
We talk about the algorithms, how smart they're getting. We talk about the data, how they've basically consumed the entire internet. And of course, the chips.
Silicon. How many transistors you can cram into a tiny space. That's the glamour. That's what sells the headlines.
Exactly. But today, I want to pivot. I have a report here that makes a really compelling case that we are all looking at the wrong thing.
Or maybe just ignoring something huge.
Yes. Ignoring a massive invisible physical wall that the entire industry is about to slam into. And it's not a lack of data, it's not buggy code, it is quite simply heat.
Ah, heat. The oldest enemy of electronics.
But this isn't, my laptop's a bit warm kind of heat. This is something else entirely. Today we're doing a deep dive into a report from the AI World Journal, published just today, January 23rd, 2026.
And what's it called?
It's titled AI Chip Cooling Systems, the hidden bottleneck of the intelligence era. And honestly, the numbers in here are genuinely terrifying.
Terrifying is the right word. We're getting to a point where the physics of cooling is actually becoming a harder problem than the physics of computing.
So that's our mission for this deep dive. We're going to unpack that. We'll explore why these AI chips are becoming what the report calls thermal extremes, or the good old computer fan is basically a dinosaur now.
And how companies like 3M are turning to, of all things, boiling liquids to keep this whole revolution from melting down.
It sounds so counterintuitive. Boiling usually means something has gone very, very wrong with your computer.
It does. But in this new world, the boiling is actually the solution.
Okay, we are definitely getting into the physics of that because it sounds wild. But first, let's set the stage. The report starts with this idea of a thermal wall. For decades, we just made chips faster, and the cooling guys kind of figured it out, right?
Yeah, you put a bigger fan on it, a bigger heatsink.
So why is now different? Why can't we just spin the fans faster?
Because the nature of the work has fundamentally changed. Think about your own computer, even a really high-end gaming PC. Your usage it's bursty.
Bursty, you mean like stop and go?
Exactly that, stop and go. You open an application, that's a spike in activity, and then you read something on the screen. The chip rests.
So it has recovery time. It gets to catch its breath thermally.
The heat has time to dissipate. But an AI accelerator, a chip that's training a huge model that is not a sprinter, that's a marathon runner sprinting the entire 26 miles.
So it's just pegged at 100%. For how long?
For weeks. Maybe months at a time. It's just sustained near maximum utilization. Yeah. The report has this great line. It says these chips aren't overheating because they're inefficient.
They're overheating because they're too effective.
Exactly. They're just converting electricity into math so incredibly fast that the waste heat literally can't get out of the way in time.
And the density of that heat, that's what got me. The report cites heat densities over 1,000 watts per square centimeter.
And to put that in context for you, that is hotter than the inside of a nuclear reactor core. In some cases, it's getting close to the heat flux of a rocket nozzle.
Okay, that is not a comforting thought. Rocket nozzles inside our data centers.
It's an unbelievable amount of energy concentrated on a surface the size of a postage stamp. And the projections for the next couple of years, for 2026 to 2028, they're talking 1 to 3 kilowatts per chip.
3 kilowatts, that's like 3 space heaters running full blast, but shrunk down to the size of my thumbnail.
And that's where air just fails. It gives up. Air is a gas. The molecules are far apart. It is a terrible conductor of heat.
The report calls air mathematically irrelevant.
No.
I thought that was pretty harsh.
It's harsh, but it's true. the math just doesn't work anymore. If you try to cool a 3 kilowatt chip with air, you'd need a fan that sounds like a jet engine, uses a ton of power itself, and it still wouldn't work. The chip would just throttle itself to death.
And throttling is when the chip slows down to save itself.
Right. Yeah, it's a safety feature. But if you just spent $30,000 on a single AI chip and it's running at half speed because it's too hot, you're just burning money.
Okay, so air is dead, fans are out. The report says the industry is pivoting to liquid intelligence. Now, I have to ask the obvious question here.
Go for it.
Since I was a kid, I've known electricity plus water is very, very bad. So how on earth are we talking about immersion cooling?
It's a natural fear. It goes against everything we've ever been taught about electronics. But the key is we're not using water. We're using something called dielectric fluids.
Dielectric. What does that actually mean?
It's just a fancy way of saying electrically non-conductive. Think of it like this. These fluids are insulators for electricity, but they're amazing conductors for heat. You could take a running laptop plugged in and just drop it into a tank of this stuff.
And it would keep working.
It would keep playing your video. It wouldn't short out. Nothing.
My brain just refuses to accept that.
Ah!
I cannot picture dunking a live motherboard in liquid.
I know, it feels wrong. But companies like 3M have engineered these fluids specifically for this. And because the fluid can touch everything, you don't just cool the main processor.
Right.
You're cooling the memory, the power components, every little capacitor. The fluid gets into every nook and cranny.
A total bath.
A total bath. And that lets you just get rid of all the complicated mechanical stuff. A normal data center is mostly just a giant air conditioner.
With raised floors and huge air handlers.
All that. You can throw it all out. With immersion, you don't need airflow, so you can pack the servers in much, much tighter, like bricks in a wall.
So you save space. But there's a big sustainability point here too, isn't there? We always talk about the electricity AI uses, but what about the water?
That's the sustainability paradox the source mentions. Those huge air-cooled data centers often use evaporative towels to cool the air. We're talking millions of gallons of water just disappearing into the atmosphere.
And immersion cooling is different.
It's a closed loop. The fluid stays in the system. You capture the heat and you move it somewhere else. And because you're capturing nearly 100% of that heat in a liquid, you can actually use it.
This is where they mentioned heating offices and things, right?
Yeah, you get high-grade waste heat. Hot air from a data center is just lukewarm. It's useless. But hot liquid, say 60 degrees Celsius, you can plug that right into a district heating system.
The future of artificial intelligence is unfolding, and it's happening at AI World Week, the flagship global event for innovation, collaboration, and transformation. This flagship global AI event is designed to connect visionary leaders, trailblazing entrepreneurs, and influential thinkers to explore the endless possibilities of AI. Experience groundbreaking technology that redefines industries and inspires progress. Join thought-provoking discussions on ethical AI, digital equity, and the transformative role of technology in our world. Build meaningful connections that catalyze innovation and drive impact. AI World Week is powered by AI World Society, a global movement dedicated to advancing AI responsibly and ensuring it serves humanity. Together, we're shaping a smarter, more inclusive, and equitable future. Continue your journey beyond the event with the AI World Journal, offering expert insights, in-depth analysis, and the latest trends shaping the AI landscape. This is your opportunity to lead, to innovate, and to transform the world with AI. AI World Week. We invite you to join us and embrace the AI revolution.
System, heat a swimming pool, you turn a waste product into a resource.
Okay, so we've got this magic fluid, we're saving water, we're saving space, but then the report goes even further. It says the real end game isn't just dunking the chips.
Right, it's boiling them.
This is two-phase immersion cooling.
And this is where the physics gets really cool. This is the frontier.
So walk me through this. Why do we want to boil the fluid? In my car, if the radiator boils, that's a very bad day.
It is, but that's because your car is a single-phase system. There are two ways to remove heat. The first is just heating the liquid up. That's sensible heat.
Okay, liquid gets hot, it flows away.
That's one phase. But the second way is to actually turn the liquid into a gas. That process is called latent heat of vaporization.
I remember this from high school chemistry. It takes a ton of energy to turn water into steam, way more than just warming it up.
A massive amount more. Think about a pot of water on your stove. You heat it up, the temperature rises to 100 degrees Celsius, but once it starts boiling, what happens to the temperature?
It just stays at 100.
It stays locked at 100. All that extra energy from the burner isn't making the water hotter. It's being absorbed to break the molecular bonds. It's turning liquid into vapor. That phase change acts like a giant energy sponge.
So if you engineer a fluid that boils at, say, 50 degrees Celsius.
You've got it. These 3M fluids are tuned to boil at low temperatures, maybe 30 to 60 C. So the moment the AI chip hits that temperature, the fluid touching its surface instantly flashes into vapor bubbles.
And those bubbles carry away the heat.
They carry away enormous packets of heat energy. And because of that pot on the stove effect, the chip's temperature just locks in at the boiling point. It stops getting hotter.
So the whole chip stays at one constant temperature.
We call it near isothermal operation, and that's huge. Because what really kills chips over time is thermal cycling, getting hot, getting cold, hot, cold. That constant expansion and contraction cracks the delicate connections. If it's boiling, it's stable.
It sounds like the perfect solution. So
Yep.
What's the catch?
The catch has a name. It's called critical heat flux, or CHF.
That sounds ominous.
It is. It's the cliff edge of boiling physics. You do not want to go over it.
What happens if you do?
Have you ever dropped a bit of water on a really, really hot frying pan?
Yeah, it sort of beads up and skitters around.
The Leidenfrost effect. That water droplet is floating on a tiny cushion of its own steam. That steam layer is an insulator.
Oh, I see where this is going.
If your chip gets so hot so fast that it creates a continuous blanket of vapor around itself, the liquid can't touch it anymore. You've insulated the chip with its own gas.
And the cooling just stops.
Instantly. The temperature skyrockets, and the chip destroys itself in milliseconds. So the entire engineering challenge is keeping the boiling in the nucleate stage lots of tiny bubbles.
You want the fizz, but not the blanket.
That is a perfect way to put it, yes.
Let's look at the timeline the report lays out, because this is fascinating.
Yeah.
It maps this out to 2035, and it seems like the whole skill set for building computers is changing.
It's moving from electrical engineering to, as the report says, fluid dynamics and surface chemistry. To build the fastest supercomputer in 2030, you're going to need chemists on your team.
And it predicts for 2030 to 2032 something called thermodynamic scheduling. The software itself becomes aware of the heat.
It has to. Right now, a scheduler just asks, is this chip free? In the future, it'll have to ask, what's the boiling margin on this chip?
So it's looking at the physics before it assigns a job.
It will literally calculate, if I run this workload, will I exceed the critical heat flux? And if the answer is yes, it'll split the job across 10 different servers to spread the thermal load.
That's incredible. The code is managing the phase change physics in real time.
The code and the coolant become one system. You can't design one without understanding the other.
Then we get to 2032, 2035 with co-designed architecture. This is where we stop just putting chips in liquid.
We start putting the liquid in the chips. It's the logical endpoint. All the heat is generated deep inside the silicon. That's where you need the cooling.
How do you even do that?
You literally etch microscopic tunnels, microchannels directly into the silicon itself. The dielectric fluid flows through the processor, not just around it.
It's like plumbing, but on a nanometer scale.
Exactly. And they're even talking about engineering the surface of those channels to have specific textures that encourage bubbles to form in just the right way.
Which brings us to the final point on the timeline. 2035. The cooling singularity.
A dramatic term, but the economics are sound. It's the point where adding more transistors is pointless if you can't get the heat out.
The report says cooling will no longer support AI progress. It will define it.
Think about it. If your chip design is 10 times faster, but it melts itself in 2 seconds, you don't actually have a faster chip. You have an expensive paperweight. The limit on intelligence becomes the limit on heat removal.
So this completely changes the power dynamic.
Yeah.
Which brings us to the strategic side. The idea of cooling as a multiplier.
This is why the big cloud providers are all over this. Advanced cooling basically creates compute out of thin air.
How does cooling create compute?
Imagine your car's engine could go 200 miles an hour, but the radiator can only handle the heat up to 100. You're stuck at 100.
Right.
If you install a better radiator, you suddenly unlock that extra performance without touching the engine. It was there all along. By switching from air to two-phase immersion, you might be able to safely run your existing chips 20 or 30% faster.
So you just got a 30% bigger data center for free.
You didn't buy a single new chip. You just bought better liquid. When you're spending billions on hardware, that kind of game it's a game changer. Cooling is now a strategic asset.
There was one last part of this that just blew my mind, and it takes us off planet. Space-based AI.
Yes, this is so important, and nobody ever thinks about it.
I think we all just assume space is cold, so cooling should be easy up there.
It's a huge misconception. Space is a vacuum, and a vacuum is the best insulator in the universe.
Because there's no air to carry the heat away.
No air, no convection. The only way to get rid of heat in space is to radiate it away as infrared light, which is incredibly slow. So if you put a powerful AI satellite in orbit,
It just cooks itself.
instantly, all that heat has nowhere to go. The only way it works is with a closed-loop liquid system like this, moving the heat from the ship to a giant radiator panel that faces deep space.
So these dielectric fluids aren't just for data centers on Earth, they're essential for a Mars colony.
For any serious off-planet computing, yes, you can't use a fan on the moon.
Wow. It really puts it all in perspective. We started this talking about noisy fans and ended up with boiling, micro-etched silicon in orbit around Mars.
It's been quite a journey, but it really drives home the central point of the report. The era of easy scaling is over.
The free lunch is over.
For 50 years, we could just shrink things. Now we have to get physical. We have to master thermodynamics.
The report's closing thought is really powerful. It says, the race for AI dominance isn't just about algorithms. Compute without cooling is theoretical.
That's the line right there. A brilliant idea on a whiteboard is worthless if you can't run it without melting the hardware.
And its final image. In the race for AI dominance, the winners will not just build smarter machines. They will build colder ones.
It just changes how you look at the whole field. A data center isn't a library of information anymore. It's a massive industrial heat exchange engine. The intelligence is almost a byproduct.
Something to think about the next time your phone gets a little warm in your pocket. There's a whole world of physics trying to keep that intelligence from boiling over.
Absolutely. Stay cool.
That's it for this deep dive. We've unpacked the thermal wall, the magic fluids, and the future of cold compute. Thanks for listening.